So with this question, which is a really tricky question, but if you read out the details, it is solvable with the tools that you have in grade 9 math. So in the diagram above, you have the larger circle, which we can tell here is essentially two of the smaller circles shoved inside. So 2x is the radius of the larger circle, whereas for the smaller circle, it's the entire diameter. So when I think about then the radius for the smaller circle, it's going to be half of that. So I'm going to write radius small. And so instead of 2x, it's just going to be x. The ratio of the area of the large circle to the area of the small circle is, now remember, area is equal to pi r squared. And when we think about both of these circles are going to have the same area formula. If I write area of the large, which is going to be pi r squared, and if I substitute for the radius, at least from what I've been given in the question, that radius is going to be 2x squared, and that's going to be pi, and then if we think about that 2 applied to everything inside the brackets, that's going to be 4x squared. You could rewrite the 4 in front, or you can keep it there. That doesn't really matter, but traditionally we tend to keep the coefficients in front. So 4 pi x squared. That would be the area of the larger circle. And then if we think about the area of the smaller circle, again, pi r squared. This time, though, the pi value, or the radius, is x. And so it would just be pi x squared. So then here is the area formula for the smaller circle. So now to get the ratio, well, we just put the area of the larger circle over the area of the smaller circle, which is then going to be 4 pi x squared over pi x squared. And remember, just like we studied in all the polynomials division, that all the terms that are like cancel each other out. Just like this, and all you're left with is 4. Now, when we deal with polynomials and tiles, it is important to understand that we simply always add unless there is a bar or a multiplication sign given between the different sets of tiles. Otherwise, in this case, there is no bar. That I just put that one in right now, but there is no bar here, so we're going to assume that it's always added. But what we will do is we will pay attention to the negatives and the positive tiles. So each gray is worth a single digit without any variable. The rectangles here are worth a single x variable, and the squares are x squared. So what we have here is we have x squared, and then plus 1x plus another x. And then finally, minus, or I should say plus this minus x from here. And then plus minus 1 plus minus 1. And so what we're going to do here, when we want to know what the value of the area diagram here is if x is equal to 3, is we got to get a simplified polynomial formula. So we're going to add like terms over here. So we're going to go x squared plus 2x minus x. So that's actually just going to be x. And then plus -1 plus -1, that is going to be minus 2. And now that we've got our simplified polynomial and we want to figure out what it is, now we're going to sub in the value of 3 wherever the x's are. So that'll be 3 squared plus 3 minus 2. And that's going to be 9 plus 3 minus 2. Remember to do BEDMAS. And that's going to be 12 minus 2. And then finally, the value is going to equal 10. So for this question, again with algebra tiles, Cooper was setting a set of algebra, or was using a set of algebra tiles as shown above. So over here and here, they just kind of tell us which color and shape correspond to what value. The following were some polynomials that he was working with. Okay, so a series of orange, a mix of yellow and orange, all rectangles and a square. The examples that model monomials. So when we simplify each of these, which one are going to result in monomials? Now remember, this is going to be one term slash coefficient. So if I add up each, am I going to get one term or coefficient? So if I look here, each of these is -1, so that's 4, 8, 12, and 16, or -16. So 1 is equal to -16, so that's a monomial. If I look at number 2, okay, we get 3 bars, which is each hold an x value. So that's going to be 3x and then -3, right? If I include these as well. So 3x minus 3. Well, this is a binomial, right? It's got 2 terms in it, so that's not going to be the case. If we look at number 3, I have now a series of 6 x valued rectangles. Each of them are -x. So you can add them all up since they're like terms. That's going to be -6x. And this as well is a monomial because it's one giant term. And then if we look at the fourth box here, we have just x squared. So, and this is also a monomial. It's one term. So it's the set in 1, 3, and 4. These are all monomials. And so we would have to go with the bottom option D over here.